For two black surfaces, we found that the net heat transfer rate between the surfaces can be expressed as the difference between the emissive powers times the product of the area and view factor. We'll see that in general, one can think about this view factor piece of this expression as a resistance. And so remember that a resistance typically is the proportionality, inverse proportionality between some potential difference. In this case, the potential difference is between the emissive powers, the black body emissive powers, EB1 minus EB2, over this resistance. And I'm going to call this a geometric resistance because the view factor is a geometric effect. And that ratio, that quotient, is then equal to the heat transfer rate. So we can generalize the notion of a heat transfer resistance even in these radiation systems by thinking about the view factor times the area as a geometric resistance. So what this suggests is that it's going to be very important for us to understand how to find these view factors because it is an important part of how to analyze radiative transfer problems. There's some relatively simple cases that we can think about in terms of understanding view factors. So take a case of concentric cylinders. So we have a two-surface problem. We have surface 2 with area A2 at some temperature T2, and surface 1 with area A1 at some temperature T1. I hope you see that surface 2 can actually see itself. So if we were asking ourselves, for all the radiation that leaves surface 2, what fraction of it hits surface 1, it would not be a simple problem just looking at it geometrically. What we have to do is we have to use reciprocity and additivity to understand this problem better. So surface 1 does not see itself, while surface 2 does see itself, and surface 1 only sees surface 2. Understanding that says that the fraction of radiation leaving surface 1 that impinges on surface 2 is equal to 1. So that's pretty clear. And what we can then do, so let's just write this down, fraction of radiation leaving 1 and seeing 2 is unity. So all of it sees surface 2. Surface 1, by definition, surface 1 does not see itself because of additivity. So we know that F11 plus F12 is equal to 1. And since F12 is equal to 1, F11 must be equal to 0. Reciprocity is what we come up with from the symmetry of the view factor integral. And this says, again, that A1 F12 is equal to A2 F21, such that F21 is equal to A1 over A2 F12, which is just equal to A1 over A2, since F12 is equal to 1. This allows us to find how much, or the fraction of radiation from surface 2 that sees itself. And clearly you see that as A1 becomes small compared to A2, so if you have a very small cylinder and a much larger cylinder, that most of the radiation from surface 2 is going to see itself, and only a small fraction of it will see surface 1. There are also other interesting approximations that we can use in terms of symmetry. So in a 3D system, imagine that we have a sphere near a large plane. What you understand is, of course, that if this is a sufficiently large plane, and this is obviously truncated just to fit on this screen, that all the radiation that comes off of this sphere either is going to go in some sense in the upward direction or in the downward direction. And if it's a large enough plane, half of the radiation from surface 1 will impact surface 2. So we need to be able to use symmetry properties as much as possible to understand how to develop view factor relationships. More generally, though, in evaluating view factors, there are several methods that are used. One is direct integration, and this is oftentimes very difficult because it involves contour integration or numerical integration of those double integrals. Statistical methods, or Monte Carlo sampling, and what this actually means is that you, for a complicated system, if, for example, you said, I have a square that I want to find out the view factor to a cylinder, what you might do is you might send off rays in many different directions from this square and ask what fraction of these actually impact this cylinder or the circle. And so it's a geometric problem and a ray tracing type problem to understand what fraction actually will impact the second object. For two-dimensional problems, there's a very efficient method called Hottel's cross-string method that is used, and we'll talk about how that's developed. And experimentally, people use a unit sphere method, and in the unit sphere method, one of the ways to think about it is that you look at a reflecting hemisphere, for example, and ask yourself what fraction of the hemisphere. So if we have a hemisphere, let's just sort of play this out, and we center it on an object, and this hemisphere is very highly polished and is marked into different regions, then when we ask the question about what the view factor is from this object to something different, something suspended above it, we're really looking at the amount of area on this hemisphere that this element will take, and that relationship can be used to find the view factor. So in general, you're not going to be using most of these methods. You will use the Hottel's cross-string method, and you'll use tables that have been made available in various reference guides. So for two-dimensional systems, the Hottel's cross-string method is the way that we're going to actually look at these problems. And the Hottel cross-string method takes into consideration that as long as we have a convex surface or convex surfaces, so by the convexity of the surface, it means that none of these surfaces actually see themselves. So if we have, as we're showing here, two surfaces, surface 2 and surface 1, we don't want a curved surface. We want just this, it can be curved, but it has to be curved in a particular fashion. And what we're asking then is, because of this, it means that for these types of surfaces, that the surfaces don't see themselves. And by virtue of the fact that they don't see themselves, some simplifications are available. One of the simplifications that's available is, as we look at this this what looks like a channel now, we're interested in surface 2 to surface 1, the view factor from 2 to 1. We see that the view factor from 2 to 1 clearly has to be the view factor, it's 1 minus the view factor from 2 through 3 and 2 through 4. And this is that's using additivity. So additivity gives us that information. It can be shown relatively easily that for an arbitrary triangle, that FAB to FAC is equal to a relationship dependent on the lengths of AB, AC, and BC, where BC is this diagonal. So what we're really doing is we're formulating two triangle relationships. We're doing a triangle, we're forming one triangle which is ABC, and we form another triangle that's ABD. And what we're expressing is that if we know the amount of radiation that goes through AC and the amount of radiation that goes through BD from this triangle relationship, then using that and additivity will give us what must go through surface 1. Said differently, this F23 is really just FABAC, so we can, this is really F23, and this is F24. And just using the geometry of these systems, F21, as you can see, can be expressed in terms of the sum of the length of the diagonals. The diagonals are BC and AD, minus the sum of the sides, which are AC and BD, divided by 2 times the sum of the original surface AB. This is a very simple and powerful way to get view factors in two-dimensional systems. Oftentimes the tables are provided, but not every single configuration is given by the table, and we have to do more than just what the tables provide. We have to use some symmetry properties, and we have to use the simple view factor algebra. And by view factor algebra, I primarily mean we have to use this reciprocity relationship and also this additivity relationship. And so oftentimes we might be given in the table, let me just finish writing this down, the view factor from surface 2 to surface 1. But we might want, for example, to subdivide surface 1 into 1A and 1B. And we want to understand how to, for example, calculate the view factor from surface 2 to surface 1B or from surface 2 to surface 1A. And what we do is we can manipulate the view factor relationships, for example, by recognizing that the view factor from surface 1 to surface 2 plus 3 is the view factor from 1 to 2 and 1 to 3. That's convenient. And so if we know 1 to sort of this global surface 2 plus 3, and we know surface 1 to 2, it would easily give us surface F13. So F13 would be F1, 2 plus 3 minus F12. And if the basic geometry of the correlation is given in terms of a block like this, that could be either surface 2 plus 3 or it could be surface 2, and we'd be fine. Sort of more interesting relationships hold. And here what we're saying is that there's some surface J where J is subdivided. So AJ is subdivided into the sum of A sub K's. So we're thinking about a surface that is parameterized or divided into multiple other surfaces where these are these K surfaces. So if we have a relationship of Fij is equal to the sum of Fik, we can multiply by Ai and apply reciprocity, where Ai Fi to j is the same as Aj Fj to I, which is Ai, so this is this Ai Fi to k. And what this implies then is that we know, using these two pieces of it, that Aj Fj to I is Ak Fk to I, and dividing by Aj, so this expression here is really Aj, because we said that Aj is the sum of AKs. So we get an interesting relationship in terms of the view factor from a multiple broken up subdivided element to some I surface in terms of the individual view factors to surface I and their areas and the total area of the elements. And we'll look at some examples of how to use things like this. In general, when you have multiple-sided enclosures, you have a lot of view factors. So even in a simple three-sided enclosure, so let's take a look at a three-sided enclosure where we have surface 1, surface 2, surface 3. Sometimes we like to think about the view factors in terms of a matrix. And so we can think about this as F11, F12, F13, F21, F22, F23. Notice the diagonal terms are how the surfaces see themselves. So F33 is surface 3 seeing itself. So we have this view factor matrix. And so for a three-sided enclosure, we have 9 view factors. And in general, for an n-sided enclosure, we have n squared view factors. So that's a lot of terms. If you think about a cube, so if you're inside a cube with 6 surfaces, that means you have 36 view factors. Calculating all these would be a challenge, but what happens is that we're able to use some of the view factor algebra to simplify and get a reduced set of view factors that we actually need. So taking the three-sided enclosure as an example, we have, for example, reciprocity, which eliminates, so reciprocity doesn't have anything to do with these diagonal terms, but reciprocity says, for example, that A1 F12 is equal to A2 F21, and that A3 F31 is equal to A1 F13, and A3 F32 is equal to A2 F23. So these are the reciprocity relationships. Notice that these are all tied across the diagonal. So what happens is, in general, reciprocity for an n-sided enclosure means that you have, and let's look at the number of equations, it has n squared is the total number of terms that we have, but we get rid of n of those because those are the diagonal terms, and we divide this by 2. So we have n squared minus n over 2 equations that are provided by reciprocity. And also for each of these sides, we have additivity. So additivity, as you know, says that F11 plus F12 plus F13 is equal to 1. So each side has an additivity equation. So we have n additivity equations and n squared minus n reciprocity equations. So when we subtract this off from the total n squared unknowns, we have n squared unknowns, but we have number of equations we have are n times n minus 1 over 2 reciprocity minus n by additivity. And this is what I'm showing here, n squared minus n minus n minus times n minus 1 over 2, which you can simplify to n times n minus 1 over 2 view factors. So really, for the case of the three-sided enclosure, we have the three-sided enclosure problem, but we have we have the reciprocity relationship for it, and we have the, so let's see, we have our 3 reciprocity, we have our 3 additivity, so we have 9 minus 6 equations, which means that we have 3 view factors that we need to know. 3 view factors needed. Now, when we have, say, a convex surface like we had in the Hottel problem, it means that the diagonals are known to be 0. And so we already started off with an n squared minus n number of unknowns, which was our 9 minus 3, which is 6. So our number of equations is exactly the same as our number of unknowns in that problem, and we can find all the view factors for that triangle system relatively simply. But the key point here is that using our reciprocity and additivity equations significantly simplifies what we're trying to do.